Next up, we're going to be talking about fundamental solution sets, which are going to be sort of the first way that we learn to think about solutions to this type of differential equation. So concerning solutions to these nth order ODEs, we're going to begin by thinking about homogeneous problems. And I know it's been a while since the beginning of class, so I'm going to write down what I mean by that. So same left side of the equation that I introduced at the start of this section, but instead of being equal to any function g of x, it has to be equal to 0. And if I need to refer back to the specific case of that differential equation, I'm going to call it like star with a circle around it. And in this special case where g is 0, we're going to know that we have a solution to the differential equation if we meet a few conditions. So first we need to find some functions y1, y2, and yk that are functions that are also solutions to the ODE. Then their linear combination I'll write combination a little bit clearer. Linear combination, which is given by y equals c1 y1 plus c2 y2 all the way down to ck yk. That's also going to satisfy the ODE. So if you can find a bunch of different things that when you plug it into the ODE, it's okay. Taking a linear combination where you multiply by a constant and add them together is also going to solve the ODE, even though that would be more of a pain to plug in and check if it's okay. And important to note here is that some of those c's can be 0, just like we saw when we were doing these examples. And then once you've found this collection of functions that can solve the differential equation, there are two conditions we have to meet to make it a special kind of solution. So if those y1 through yk have two properties, then that linear combination is going to form the general solution to the ODE. So these two properties, I'm going to tell you, if they're true, you can find every possible solution to the ODE using those functions y1 through yk. And those conditions are going to be, first of all, we have to have linear independence, or that they are linearly independent. And the definition of linear independence is that if we took that linear combination and we set it equal to 0, then the only possible solution would be taking C1, C2, all the way down through CK equal to 0. I'm going to switch the page real quick, so pause if you need to. But that condition ends up being not especially helpful. So an easier to check condition is going to be using something called a Wronskian, denoted by W. And it can be defined for some functions y1 through yn. And what you're going to do is you're going to put your functions in the top row of a matrix. And then you're going to put their derivatives in the next row. And then you're going to go all the way down until you reach the n minus 1th derivative for n functions. So this ends up being a square. However wide it is, it has to be that tall, and you just take increasing derivatives until you have a square. And then those vertical bars I've drawn mean take the determinant. If you've taken linear algebra or saw linear algebra in another class, you know how to do that. If not, you'll get some practice with it as we start doing these problems. But we want to make sure that that determinant is non-zero. And so the words for this condition would be that the Wronskian is non-zero. And then it took a while to tell you that condition, but I promise the second condition is much easier. So 2b, second condition, is that we just have to have the correct number of functions. So we need exactly n functions to form a general solution. So that means that that letter K I used before actually needs to be n, the order of the differential equation, or that I would have functions y1, y2, all the way down through n minus 1, y sub n. And then if both those conditions are true, we're going to have a general solution. And I'm not sure I could get through an example in just a few minutes, so I'm going to go ahead and hit pause, and then in the next video you'll see an example.